Hello and welcome to Disseminate the Computer Science Research Podcast. As usual, Jack here to take you on this journey. Before we do start, I'd like to give a shout out to our sponsor, PomTree. PomTree are the developers behind Raftery, the open source temporal graph analytics engine for Python and Rust. Raftery supports time traveling, multi-layer modeling, and comes out the box with advanced analytics like community evolution, dynamic scoring, and temporal motifs mining. It's blazingly fast, scales to hundreds of millions of edges on your laptop, and connects directly to all your data science tooling, including Pandas, PyG, and LangChain. So go check out what the PomTree guys are doing at www.raftery.com, where you can dive into their tutorial on their latest release. On to the show. So today is another installment of our high impact series for the listeners who are new to this type of episode. It was originally inspired by a blog post by Ryan Marcus on the most influential database papers. And today we are going to be speaking to Andreas Kipf, who has the #1 spot for 2019 with his paper on learned cardinalities estimating correlated joins with deep learning, which was published at that year's edition of CIDR. Andreas is a professor at the University of Technology Nürnberg. Before that, he's worked as a senior applied scientist at AWS in their Learn Systems group, where he was one of the founding members. Before that, even he was a postdoc at MIT's Data Systems group, and before that, he did his PhD at the Technical University of Munich. Andreas's research interests are, and you can correct me if this is wrong, Andreas, but you like to improve systems with machine learning with a focus on index structures, storage layouts, and query optimization. Welcome to the show, Andreas.
Yeah, so glad to be on the show. Thanks, Jack, for the invitation. Looking forward to our discussion.
Fantastic. So I gave you a very high-level sort of overview of your career so far there when I introduced you, but help us colour in between the lines a little bit and tell us more about what that journey was actually like and, kind of what led you to become a researcher.
Yeah, so I would go back a few years in time. So during my graduate studies, like during my master's at TUM, I did a master thesis at UC Berkeley. So that was like sort of an exchange I did. And I was part of a collaborative research group over there. And I was really inspired by, how people approached research. So my advisor back then was Professor Eric Brewer, who was also at Google at the time. I was very inspired by, how people worked in groups on collaborative projects, not only at UC Berkeley, but also with people at UW in Seattle. And I really enjoyed that part. So basically, I changed my mind a bit because in the very beginning, when I started studying computer science, I always wanted to become a software engineer at Google. And so funnily enough, like during my PhD at TUM, I ended up doing a couple of internships at Google, and so I also got that experience. It was really, really interesting and inspiring as well. But I always had this, research in mind, and I always wanted to go back. So, so eventually, as I said, like I did my my PhD at TU Munich, did these internships, and my goal was still to become a software engineer for some reason. But then, and I think we'll talk about this later, my research turned out to be, a little bit more successful, and it got really inspiring to be in the research community and to have your own projects and so on. So I still worked with Google. I'm also in the later stages of my PhD. We created also some publication together, and it was all great. But I think the main turning point was really when I gave when I was in California for my talk about learned cardinality estimation, and I talked to Tim Kraska over there, who I did a postdoc with later at MIT, and he was basically asking me, if I would want to join MIT as a postdoc, and I always had this dream to go back to the US to one of these groups, and so that's how it started.
Awesome stuff. Yeah, it feels like you got to experience the best of both worlds, right? You kind of had kind of one foot in each camp, kind of throughout your studies and kind of getting the experience, and that's kind of. And I like what you're saying about the appeal of the kind of the collaborative nature of research and academia, and how kind of rewarding that can be as well. So I can definitely see how you've swung back towards being in research rather than in primarily in software engineering. So let's talk about learned cardinalities then. So tee us up with some background there. Give us some of the background information that we're going to need to talk about this paper today.
Yeah, so learned cardinality estimation. So basically it's about SQL databases and query optimization specifically. And I think the main idea is really, can we improve, the estimation of result sizes of SQL queries and intermediate results using machine learning? So that's like the research question we asked back then. And as it turned out, you can have a rather simple model, I would say, and apply it, to this problem, dedicate some training time to it, and get pretty good results out of that. Yeah, so that's like the the high level idea. And I think one of the reasons we decided to work on that is that query optimization is a complex problem. It consists of many sub problems, or few sub problems, I would say. So one is you get your query in, and you gotta estimate, or basically you gotta explore the search space for your query plan, right? Like, for example, if you have 3 tables that you want to join, A, B, C, you could first join A and B, and then C, but you could also first join B and C. So to decide on such a plan, what you typically do is you enumerate possible plans, and then you cost them. So the first component is this join enumeration component. The second one is the costing component. And then the costing component typically consists of a cost model. And the cost model would take these cardinality estimates as input. So for example, if I would have my query A join B, I would want to know, how expensive is it to execute. Typical, very simple cost function people use is the cout cost function, which basically just counts the number of output tuples of that particular join. And and that cost function has an input, which is the cardinality estimates, which we need to compute and provide to the cost model. So it really starts with estimating how many tuples qualify my join. So if, let's say, I have table A with a predicate like x equals 5, I would want to know how many tuples would qualify. What would be the selectivity of that scan? Same for the scan on B, and then like these base table estimations are usually pretty simple. So I would say to estimate something like x equals 5, or even some complex string predicates, like you have names and you want to know how many people start with an A. That's usually done, or pretty easily done, using sampling. So you just take a sample of your database and compute the selectivity on the sample. And then you would extrapolate to the whole table. So that's usually doable. It gets more complicated with joins, and that's the specific problem we targeted. With learned cardinalities. So basically, with joins, you get correlations in between tables, and so that's something machine learning is known to be good at, capturing correlations. And typically in databases, this is implemented, using simple formulas like, you could, for example, assume independence between these inputs. So that's, I would say, the background. And actually, something I really wanted to talk about is how this all started.
Yeah. Tell us about the origin story.
Yeah, so that's actually, yes, really, really interesting, I would say. So it's not like, how you would normally approach a paper. At least I think, most people wouldn't approach it like that. So as you remember, or as, our listeners might remember, it was, I think, around in 2018 when this entire, machine learning for systems, topic came out. So we saw a few first papers on like knob tuning, and most notably learned indexing, which created a lot of hype around it. And then also, some work on query optimization. So I was in Munich, with the database group back then, doing my PhD, and we would all discuss, the papers that would come out, and so we thought, what could we do in that space? Is there actually something in it? How does it compare to more traditional approaches and so on? So where should we really apply machine learning? So we basically started brainstorming that, right? As probably every group did at the time. And and I think our outcome was that, our conclusion was that many of the problems in databases can be solved exactly. Like, the joint enumeration problem I mentioned is something you can solve exactly up to 10 joins. If you have a cost model and you trust that cost model, the joint enumeration part can be solved using traditional, or let's say advanced algorithms. Whereas cardinality estimation, as I just explained it, like finding out how many people's names start with an A, or let's consider the Internet Movies database, which I used in my work. How many actors, how many German actors participated in French movies, for example, right?
Yeah.
That's a very tough problem to solve, and it's a fuzzy one. So it's not like that there's one correct solution, or only one correct solution. But if you get close to the correct solution, it's already probably good enough for the task. So it's rather a fuzzy problem, and we all know that machine learning is really good at these fuzzy problems, right? I mean, it often, or like rarely, provides the exact answer, but often it gets very close. Like these models, like regression models, they would get pretty close to forecasting, or just fitting a line, right? So that's one thing. And we also, said like, cardinality estimation is this really hard problem that researchers have worked on for many decades in the database community. So why not try that? So that's how the motivation came along when we still didn't have a solution. But the thing is, and that's like, for me at least, the most fulfilling one is that I have a brother working in like, he's not only my brother, he's also a deep learning researcher.
Oh, really? Okay. Convenient.
So so that was very convenient, or is still.
Yeah.
So basically I explained that problem to him and said like, we need a model that can capture these correlations between joins, right? And he basically immediately said, there's a model that just came out was released in Europe's at the time, called deep sets. So it's a neural network architecture that can that basically has set semantics. And SQL also has set semantics. So like, it doesn't matter, for example, like our query plan, right? Like, it doesn't matter if I first, join A and B and then C, the output of that subtree, like in terms of how many tuples it produces, is always the same no matter which plan I use, right? So it's so the cardinality estimation problem by itself, has set semantics. At least that specific problem that we targeted. So there was the perfect model for it already. And one limitation was still that this original model was built for one set. And we actually needed multiple sets. So we needed one for joins, we needed one for base tables. And so my brother, Thomas, sat down with me and we created a new model, which would, consider all these features, have different set modules. I would, set up the benchmark, provide the feature set. And that's how it ended up being created.
That's a fascinating origin story. Kind of it was a family affair sort of thing. That's brilliant, and I guess that's why it gets its name of like multi-sets, right? Because it was kind of taking the idea for a single set, and now we've got multi-sets, right? So that explains the the name of the network. So let's talk a little bit more kind of about how the multi-set convolutional networks actually work then. So like, what's the secret sauce behind them for being really good for solving this problem?
Yeah, so I think the main intuition is really the set semantics, right? Like, so you don't waste any model capacity on remembering, permutations, because they're just not important. So it's really about the set aspect of it. So you basically get a good, it needs fewer data samples to converge, because it doesn't, need to learn that, it's actually permutation invariant, like what we are training on. So that is one thing. But, the model is always, and it's always like, in the center of a lot of research. And I still think the model is important. But what I think is even more important is the features that you select, right? So getting the right training data. And I think there, like, we had this insight that we should not only train on SQL features, right? Like, so let's say, you have your from clause, you have your where clause, your base table and the join predicates that you could use and sort of featureize and input to the model. So that's one thing. I would call this sort of the static features that you get with your SQL query, with your SQL string. But then there's also like these dynamic features or runtime features, I think they're called in the paper, which, as the name implies, you would only be able to collect at query runtime or optimization time. And I think that was the main finding, that we should also use this runtime information. And I think, so I talked about sampling earlier, right? When I talked about base table, or when we discussed base table scans. So what a database system, like a classical one, would do is it would take these samples, right, and then execute predicates on these samples. And with MSCN, we did not want to really compete against that, but instead we said, let's use it as additional feature input. So we still do all the traditional cardinality estimation, but we input it as additional features into the model. So we basically learn, if the fifth tuple in my sample qualifies, how does that affect our output? And we basically show that the model can capture this information, basically the runtime information that we get, and that would improve quality significantly. And that's how it came along.
Awesome. Yeah, that leads into the kind of the question. I mean, I know it was 5 years ago now, so maybe you don't remember exact numbers, but how much better was it than the traditional approach?
Yeah, so I mean, and that's always the problem, right? It always depends on your on your train and test split, I would say. So why we didn't, test on the training data, we still, we tested on a constrained space, right? So basically all the training and test data, was generated, and then we did our train test split. But the test data would still follow a similar distributions. For example, the test data would not contain completely different predicates. Like if, in our case, back then we only supported equality in range. So we wouldn't add, like predicates to the test data. So so it was a constrained setup. But for that constrained space, on IMDb, I think it was like 6 tables back then. It was, up to an order of magnitude better than what you would get with, more traditional approaches. The downside, of course, was that, you had to train it. So I think that was the main limitation, that, it took a while to train. You needed a lot of training data. And at the same time, once you trained it and your data would change or your workload would change, you might need to retrain it again. So we didn't have update support at the time. So and that said, I think, back then for this constrained problem space, I think we did really well. But then, we also discovered a lot of limitations to make it really practical.
Yeah. I guess, did you ever find the answer to the question of how many German actors played in French movies?
Well, actually, I I just came up with this one. So I don't know, but we asked many of these. Yeah.
Yeah. No, but that's awesome.
Project.
Yeah, it feels like you said, that you were kind of aware of the various limitations with it, but it sort of was a nice, was well scoped and led the groundwork for a lot of future work then. So I guess let's talk about the impact that this paper has had over the past 5 years since it was published, and have many of these shortcomings been addressed?
Yeah, so it's crazy how time flies, like you just said, yeah, 5 years. I mean, that's crazy. But yeah, so there has been a lot of follow-up work actually, addressing our limitations. I was involved in some of it, but only very limited. So there have been, many papers, for example, addressing updates, which was one of our main limitations. I still wouldn't say it's solved yet, just because it's a very hard problem in machine learning in general, right? It's not something very specific just to databases. I mean, we of course we can collect new training data and so on, but you still gotta update your model and basically make sure that your model sort of scales to your new feature dimensions and so on. So so there's not you can do there, I think. So yeah, there's still some update cost for sure. On the other hand, people showed that in some cases you might actually not need a deep net for it, right? So you can actually use simple gradient boosting techniques to get pretty close. You might not be able to outperform it, but you can at least get pretty close. And then one other limitation was around low selectivity cases. Let's say I select an actor in my Internet Movie Database who only participated or played in a single movie, right? So I might not have seen that person during training. So it might be very hard to estimate what that actor, how many movies the actor participated in. So that's something we cannot really, solve with a supervised approach like MSCN is. So yeah, so there have been a lot of follow-up works in the unsupervised space as well, like Naru and DeepDB, just to name two of them, which address specifically these cases. So they basically train an autoregressive model over the entire input, so they would have seen those rare cases as well. Yeah, and finally, I would say string predicates is something we didn't handle, so there have been a few follow-ups. Uncertainty estimation is something which you actually need before you deploy something like this in production, because otherwise, how do you know if the model performs well enough to be deployed? So that is something a few groups worked on. And I think there still needs to go more research into that to be able to trust these models fully. Because up to date, they haven't been adopted by many of the big players. So there's one example in Microsoft Azure Cosmos DB. They implemented a similar approach as far as I'm aware of. And also there are other database companies that are implementing similar approaches still today. But so they're usually very careful with, and which makes total sense, right? I mean, you don't want to ship a model where you're not sure that it performs well.
Yeah, you preempted one of my questions there. It was going to be, has any of these techniques found their way into commercial systems yet? But I guess they're still sort of finding their way and gaining confidence in these techniques and the stability of them before they unleash them on the wild, I guess. Quickly on the gradient boosting aspects you mentioned as well, you can kind of get a lot of the way with techniques such as that. And I guess is the benefit of a gradient boosting that they are quicker to train as well compared to like deep network, because that's kind of the main advantage of like the training time's a lot smaller.
Yeah, so that is one advantage. It's also smaller, so it might better fit into RAM. But I wouldn't necessarily say that the training time of the model is the big bottleneck in low cardinality estimation. I think it's much more about training data collection. For example, I mean, of course, like if you're a big player, like one of the big, cloud data warehousing companies, I mean, you basically have all of this training data already, right? Just because you have this large customer base, and you can potentially, train a model maybe for each customer on its own, or maybe you can do something, in an anonymized form across customers or something like that. But typically, if you don't have that, you're basically starting from scratch, right? And you got to sort of cold start and deploy your model. So the thing, like the approach we followed is we basically try to, we back then hard coded the important joins, but what you could do is you could, just get that from the user. And then for the important ones, you actually collect training data. So you execute queries in the background with different predicates. You get all that training data, sample the entire search space, and then, train your model on that. And I think in that case, model training is really not the bottleneck. It's much more about training data collection.
I had another question bouncing around my mind. What was I going to ask? Oh, yes. It was about the, as sort of the data, the workload's changing, and maybe the models, the accuracy decreases over time. So you need to do this sort of collecting new data, retraining process. This is maybe very workload sensitive or data sensitive, but how quickly can things become stale? Is it just what is it a function of primarily of how quickly your model's accuracy drops off as the data or workload's changing? Or is it, like I said, workload dependent?
Yeah, so it really depends on your data and workload changes. So for example, if someone adds a new column to your database, there's not much you can do about it, right? You haven't seen that predicates on that column before. Likewise, if you add, 10% new tuples, which follow a completely different distribution, there's also not much you can do. But in my experience, data usually follows the same distribution, right? Like a sales database won't suddenly contain weather data. Well, maybe it might, but but I would say it's usually following a similar distribution. So usually it should be good for a while, and there have been a few papers studying this exact question. But yeah, again, it really depends. So for example, what the model does is it normalizes column features. So basically, when I have a predicate on a given column that, would say, same example as before, x equals 5, and the column domain for x is between 1 and 100 at training time. But now at test time, people ended up inserting values up to 1 million, the model wouldn't be able to guess that. So yeah, so it really depends on the kind of changes and if they're breaking changes, I would say.
So after the learned Cardinalities paper, you then went on to do a postdoc and then eventually going on to work at AWS in their learned systems group. So tell me about how that paper then led to that. And then I guess after you were at AWS, you kind of came back to the University of Nuremberg. So yeah, tell us about that story a bit more.
Yeah, so basically after I submitted and published the learned cardinality estimation work, I wrapped up my PhD at TU Munich, joined MIT, and so I worked with in the beginning with Ryan Marcus and Tim Kraska. That was how it started on this SageDB prototype, which is, so for those not familiar, it's basically a system that tries to implement different learning techniques in a coherent way. So so we ended up doing some storage optimizations. Ryan worked on some query optimization aspects, and we created a research prototype. And so that went on for a while, and then eventually we decided, we could have most impact in industry because we're simply lacking workload. So, and that's, I think, still nowadays a big problem. Like in academia, you don't really have access to the real problems. So we decided we could have most impact in industry with these kind of techniques. Yeah, so we joined the SageDB group joined Amazon, and we founded the Learn Systems group led by Tim Kraska. And over there, it was actually very interesting to see how the real problems actually look like after we solved the not so real ones in academia. And so we get access to workload statistics, and we're able to build sort of new solutions in for example, in the storage space, and also in terms of workload forecasting at AWS and specifically at Redshift. Yeah, and that was really inspiring. And I think I got a lot out of that time.
So you're at Amazon and things are going well. You've got this new group you founded, and you've got all this access to all these nice real workloads. You've seen behind the curtain to all, and got access to all this really cool data and stuff. So then you kind of then went back to academia, and you ended up back at the University of Technology in Nuremberg. So tell us how that happened.
Yeah, so that's a very interesting one. So I've been following the creation of UTN, which it is called for short, for many years now. So it's it's a second technical university in Bavaria, next to TU Munich. So it was it's a big project by the Bavarian government, and it's been many years since the last one was founded. I think it was 40 years ago. The University of Passau, so another one in Bavaria. So yeah, it's a big thing, to have a new university. So you don't get this chance, multiple times in your life, I would say. Yeah, so I was very excited from the beginning on about the creation of this, new buildings, new campus, new everything pretty much. And yeah, I mean, on the other hand, with every new place, there's a lot of work. So you gotta, build it up first, and there's probably more work than you would have in other places. But yeah, I see it more as a chance. And so it was sort of in the back of my mind for many years already to get a spot, get a research position at this place. And it was also one of the reasons why I decided to do that postdoc at MIT, because I had this idea in mind, and I was like, if this comes around, I would pursue academia. And so basically, I saw the opening, I applied, and I got the offer, and I just couldn't resist.
Fantastic. Yeah, it must be really nice to have a blank slate to kind of go and create something. So yeah, while it is probably a lot of work initially to kind of get things off the ground, it's just like an opportunity you'll probably never get again, right? They don't make, like you say, they don't make universities every day, right? On your universities. So yeah, that's fantastic. So I guess kind of, yeah, what are you working on at the moment at UTN?
Yeah, so some of the learnings at Amazon were, that, we are basically working on the wrong problems, as I said, in academia. And it's a lot about, I think it's a lot about usability of these systems. And you might, know that from your experience at Neo4j. If people cannot really use your system, you can optimize performance however you want. It just doesn't matter, right? At the end of the day, doesn't mean that performance isn't important. So I still would say performance is a very important aspect, especially the cost component of it. But I would say, one of the most important things is you want to make it easy to use. And this is actually something which, I discovered during my first class that I taught at UTN. And so basically I had an exercise with my students where they had to import some log files into a data warehouse. And I was basically, helping them out and seeing how they're doing. And I found that, they were basically, manually creating, table statements and so on. It just took them a very long time, and they had they basically just couldn't really import it, in the given time, right? There were just too many edge cases to consider and too many questions being asked. So I just thought, would be great to automate this process. And nowadays with generative AI, I think it's a great chance for us to create easier user interfaces to automate a lot of this. And so we basically started a project that would ease the data loading aspect. And I think my vision for that is that you just have, you just give it an S3 URL and with some, Parquet, CSV, JSON files, whatnot in there, and it would just automatically figure out everything for you, right? It would basically suggest some schema. It would, tell you, that's the data you should look at. That's how you should import it. That's the system you want to use. and all of that, and ideally with some, I mean, not ideally, but possibly with some LLM interaction to basically have the user in the loop.
Yeah, honestly, you hit the absolute nail on the head there with like kind of data importing being like one of the most horrible experiences in the world. And there's so many times I've come across I'm like, okay, yeah, I'll fire up an instance of this, and then I spend the next 3 days trying to get the data into the damn thing. And I think a few of these grey hairs I'm getting are because of that. I think over the years, but you are right as well that I think often in academia we're very much focused on performance, whereas there's the other dimension of usability, right? And it being easy to use. Obviously, like you said, performance is very important still, because when you get to use it, you want it to run fast, right? Anyway, but that sounds fantastic. I look forward to seeing the results of that research. Cool. So let's kind of take a little retrospective now and kind of look back over your career today. And what are you most proud of in your career?
Yeah, I think I would probably still name the cardinality estimation work, and not because it's the most difficult or most impactful one out there, but simply because of the fact that it was done together with my brother, and this is just something very special to me. And it was also a process that I really enjoyed. So yeah, this is the number one.
Yeah, I can definitely see that. It must have been super nice to work with your brother on that. And do you still actively collaborate? Because I mean, obviously, there's still a relative amount of overlap between your two fields of interest. So yeah, is it something you're kind of gonna do more in the future?
Yeah, so I wish I could actually. So back then he was, still doing a PhD at the University of Amsterdam. But now, he's at Google DeepMind. So he's busy doing fancy stuff.
Yeah. Okay. Cool. Always good to have those contacts, though, right?
Yeah.
Cool. We can jump onto sort of a section on motivation then, and sort of what's motivated you over your career, and what are or if there are any sort of specific papers and people who have motivated you or throughout your career.
Yeah, I would say the learned indexing paper by Tim Kraska is probably the one that influenced me the most, or that had the most impact on my career, just because I got inspired by it, right? To do the cardinality estimation work, to do something in the learned index space, and also which then led me to eventually do a postdoc in that space with Tim Kraska. So that was, I would say, the most impactful one on me personally as well. And otherwise, I mean, I was fortunate to be part of a very strong group at TU Munich, led by Alfons Kemper and Thomas Neumann. So I was also very inspired by their work, and especially Thomas' creation of Hyper, the in-memory database system, got acquired by Tableau back then, and many of his papers were very influential at the time. So for example, one that I remember is the adaptive optimization of very large join queries, which I found very like a very nice read, and I recommend it to everyone to take a look. Which he basically showed that up to 10 joins you can get exact answers in join enumeration, which I think is a great result. And so I think I was mostly inspired by the people around me. I was just fortunate to be at TU Munich.
Cool. Yeah. So I guess kind of going off motivation and sort of things like this, what's the best piece of advice anyone's ever given you?
I think it's really, that, you should not expect your projects to all work out, right? It's really like research should be about, trying out crazy ideas. That's why we are in research. if the ideas, wouldn't be crazy. I mean, we could also, be in industry, which is, not a bad thing. But in industry, you want to make sure that things actually work at the end of the day, and you have, customers paying for it. And that's like this main privilege that we have in academia, that we can try out crazy things. So I would say, like the best advice I've been given is really to be adventurous and try out things, even if they don't end up working in the end. Just try it. And I mean, eventually, something will stick, and it might be a success. It might take a while, but being optimistic and trying out crazy things, I think that's the main advice I've been given, and I need to do more of that. I think everyone needs to. We are all a bit conservative now and then, just because we wanna get publications out and get things done. But having that moonshot project, I would say now and then, I think is a great advice. Yeah.
Nice, yeah. Just keep iterating, and I guess when you're in academia as well, you have the freedom to do that, right? You're not at the mercy of shareholders like you are when you're in industry. So yeah, awesome stuff. I like that. It's a great answer, and that's a nice. You kind of touched on a few things there, which is a nice segue into like the next question I want to ask you, and that's about it doesn't always work first time, and there are setbacks and things get rejected. So I want to ask kind of what your process is for dealing with that.
So, I mean, first of all, I would say, you get better, like in that aspect over time. And I think I had many setbacks throughout my, professional, but also personal life, as everyone, has it. I mean, it's just that people don't talk about it, but, the more experience you gather, the more setbacks you will also gather. And I think, the most important thing for me is that, again, is to stay optimistic and to stay positive. So if your paper gets rejected a couple of times, and I had many rejections throughout my PhD and also postdoc, and just stay positive. And one thing I like to say is every downhill is followed by an uphill, and I think it's just, it's just important. You just want to make sure to take enough momentum with you on the downhill, to, have a good uphill. So, I think that's my approach to it.
Yeah, so just gonna ride the roller coaster, right? That's it. There's always another wave coming along. So just make sure you've got enough momentum and you'll be just fine. So no, I like that. Great. Cool. My next question, Andreas, is this is actually my favorite question that I always ask to my guests on the show, and it's about the creative process. And do you have a systematic approach to idea generation? And then once you have generated a set of ideas, how do you then choose which ones to pursue? What's your approach to that?
Yeah, it's also a very good one. So, and I don't think I have, the approach for it. So I'm still learning, and I've been so far, I've been, inspired a lot by people around me. It's, sometimes it's your own idea, sometimes it's someone else's idea. So, but I think, and that already brings me to my answer, is the important thing is in that process, at least for me, is to work with people, right? To basically brainstorm with a group of people, ideally from different fields. So because, if you just talk to people in databases, they would, probably all have a similar opinion. But if you suddenly talk to people in machine learning, they might, have some new ideas, or there might be something very interesting on that intersection. And that's actually something really nice now at my new place, UTN. So I'm basically, the only systems professor there at this point, and everyone else is in AI and machine learning. So so it's really easy to work with AI researchers right now. They're very approachable, and the brainstorming it really works. It takes some time to in such an interdisciplinary setting. I mean, it's still, computer science, but there are still some differences in how research is done and what is interesting, what not, and also the background, their background in systems, my background in machine learning, and so on. But yeah, I think this interdisciplinary approach is the right one for me, at least, and especially given my current circumstances with the new school. And yeah, also like to involve my students in that, in the idea generation, because I think one of the most important things is that you basically have ownership of the idea. And I think students are most motivated if they, basically contribute in that stage already. Right. I mean, if they were just given some tasks to do, this is not, really inspiring, right? So you should basically give them the freedom to participate in the brainstorming, have their own ideas, work on their own ideas, and that's how people will, be successful.
Yeah, I like get that early stage buy-in right from them. So yeah, no, that's a lovely answer to that question. So yeah, my next question is about the interaction between academia and industry, and obviously you've got a very good perspective because you've experienced both. And I wanted to get your take on what you think the current interaction is between these two different groups at the moment, and how that can be improved going forward.
Yeah, so this is something which I really care about, and I think there's a lot that can be improved. Just because, as I said in the beginning, I mean, research is just too decoupled right now. And, this might be fine for theory research, but it's not fine, or at least not, not what we want for, data systems research, which is, something very practical by nature. And we should be thinking about, technology transfer and so on. And yeah, technology transfer just wouldn't work if you work on the wrong problems in academia. I think it's really important to have many interactions with industry, and to enable such technology transfers. And especially in my research, where in ML for systems, where you need access to data and workloads, yeah, you just cannot do the same research in academia without industry. So yeah, so I would say it's really important to have these projects. We as academics, we should do sabbaticals, go to these companies for a while, come back, work on their problems, and just have more exchange. However that's being done. There's obviously, legal restrictions and so on. But we gotta push, and we gotta, try to find solutions to that. And so that's one aspect in, like just how to work together. But I would say there's also something on the more technical side. So it doesn't just mean that we need to basically optimize for their workloads, but if we build something, it should also be something that at least can be transferable, in the future at some point, right? It shouldn't be that, we work on some prototype which is not practical at all, or would take forever to integrate into their systems. And I think the way out there is really to invest in open standards. And I think Apache Iceberg, so the data lake format is a good example. We should invest in these. And then, we can sort of, decouple again and work on these problems independently. But then, when integrating it, it's not a big deal. I mean, it doesn't mean that it has to be directly transferable and useful, but at least we should make sure that we don't go in totally different directions. So that's that part. But at the same time, and that's something we discussed before, right? Like, we should not just work for industry in research, right? I mean, there should be some interaction, but it shouldn't be that we only focus on that. There should also be enough time in academia to do these sort of moonshot projects, right? Which might not be very practical today, but they might be practical in 5 or 10 years. And I mean, if you just think about large models nowadays, right? I mean, it's not a commodity, to train such a model, but it might be in a couple of years. So and in research, we can already think about, what would happen then, and how should we change things.
Everyone's been told now we need to go ahead, we need to do this, we need some time to work on our moonshot projects. We also need to work closely so we can get access to that real world data, and people taking sabbaticals, and just kind of sharing more between each other, being more open, and people getting exposed to both different settings. I think is definitely the way to go for sure. Cool. So let's talk about the future as well, then, while we're on this sort of topic. And what do you think are the sort of the most exciting advancements? I mean, I can maybe think of one or two already, these large language models and Gen AI and all things in that sort of space. But what is the most exciting advancements for you that you've observed recently?
Yeah, I think that there's not much more to add, because it's really about generative AI. Like, everyone is thinking about it, and especially me being at this new school now with all the AI researchers. I mean, there's just so much so much interaction you can do. And you can, basically, you can go two directions, right? You can think about integrating them into data systems, making them easier to use, for example. But you can also think about, speeding up model training and so on. And that's also something we started looking into, like, how can we help them with our system knowledge to accelerate or improve their systems? And I think one example is, in training, I mean, you basically got to keep all the model weights in GPU memory, right? So there are many quantization techniques out there, and so that's like a little project that we just started, to look into how can we, compress these weights even further with the knowledge we have in databases. So that is one thing. But I mean, especially now at UTN, we also have a lot of people working on robotics, and that is something I never thought of before. But now, when I go into the office, I mean, I see those robots, right? So you get inspired by it, and apparently there are also foundation models for robotics nowadays. So you can basically train a robot on huge data sets. And basically, simulate its behavior and then transfer it to a real robot. And so they also require a lot of training data, a lot of video data, and so on. And I'm also thinking about how can we help them to basically speed up their training pipeline and make these systems more efficient.
Awesome stuff. Yeah, it feels like we're at a very sort of critical juncture for Gen AI, and I kind of wonder what the world's going to look like in 20 years. And I mean, you look back and kind of how the internet's changed the world, right? I mean, you wonder in what way is positively and maybe negatively as well that these Gen AI systems or Gen AI is going to change the world. It's going to be interesting to see for sure. But thank you so much we'll end things there, Andreas. Thank you so much for coming to talk to us today. It's been a fascinating chat, and I'm sure the listener will have thoroughly enjoyed it.
Thanks for having me, Jack. It was a pleasure.
Fantastic. We'll end it there then. So thank you very much for coming on, and we'll see you all next time for some more awesome computer science research.